What I want to do in this lesson is get into the definition of a pure function. And the reason for this is that because understanding what a pure function is really important to understanding functional programming. So the way I define a pure function is like this. A pure function is one whose only parameters come from the outside world are the input parameters that come into this. So that's where I call it the function's front door. And what I mean by that, let me start a REPL up over here. So what I mean by that is if we have a function named sum, the only parameters that come into it are going to be right here, like that. So we're going to take in the input parameters I and j, and then our algorithm is only going to depend on I and j. And specifically what I mean by that is we don't have something else like this where you have a val name foo like that. And then if we go back up to sum, we say, well, actually what happens here is we get sum from somewhere else. Sum doesn't come in the front door. It actually just sneaks in the side door over here. This is not something we do in functional programming. So to be clear, we do not do anything like that. So I'll get rid of that. We could call that one sum-ish or something like that. So if we do that, or how about sum bad, something like that. We don't do this type of thing with pure functions. The only parameters that we want to work with in the body of our code are those parameters that come in through the front door here. And that's what I mean by this first statement right here. Another thing that happens is we do not modify input parameters that we're given. So what I mean by that is if I come over here and paste this in, we do not try to modify these input parameters that we're given. So here, we're given names as a sequence of strings. And one thing we don't try to do is say, well, names, I want name 0 to be equal to Al, something like that. This is not something that we do in functional programming. And the cool thing about that is the seek right here is immutable. So that means it can't be changed. So we can't even write that type of code. If you use a seek or a list or a vector in this spot right here, you won't even be able to think about doing that. So that's a really wonderful thing about that. Then the next bullet point here, we don't modify hidden variables that we might be able to access through side doors. So if I had left that foo variable over here, we wouldn't do something like, let's see if I can get back to it there. So I wouldn't do something like this and say, well, now I want, foo to be equal to, I'd do that on a separate line. Now I want foo to be equal to 0. And then I would do I plus j as a result here. We don't do that type of thing. And fortunately, I defined foo as a val earlier, so I can't even possibly do that. But what I mean is that we don't do anything like this inside of a pure function. So that would be a no-no right there. We also don't communicate with the outside world. So pure functions don't have any I/O whatsoever. No file access, internet database access, no quantum entanglement, nothing like that. And I will show later what we do with I/O functions. But for right now, it helps to think that pure functions have nothing to do with I/O. An important thing is that pure functions always return the same output when they're given the same input. So now if I go back here, let's say we modify foo and say, okay, it's 42. Now we'll make it a var. And then we come back to sum bad. Let's go back to this one right here that has foo. So now you see that if I call sum bad and I give it 2 plus 2 right now, I'll get 46. So right away, that's wrong. But what would happen here now is I say, well, I want foo to be equal to 11 or something like that. Now I call sum bad again. And now I get a totally different result. So here I passed in 2 and 2, and I got 46. Here I passed in 2 and 2, I got 15. Right away, that tells you something is really wrong. And that is violating this rule right here, that a pure function always returns the same output when it's given the same input. So again, 2 plus 2 should always be 4. Another key about pure functions is that they return output for all possible values. And a classic way of showing this one is a divide function. So we might take the numerator here as an int and the denominator as an int. And then we're going to try to return a double from there. And then we'll say numerator divided by the denominator. And we have that. So that will work in some cases where we say, well, how about if we have 2 and 1 and we want to do that? And it won't work when we do that. Okay, so that throws an arithmetic exception. So this is what I mean by this one. This function right here does not return an output for all possible input values because it fails right there. And the last part here is that pure functions do not throw exceptions. So I showed how this could throw an exception. So our code doesn't do that. And also, we do not try to fix the problem this way. We don't say, Well, what I want to do is I want to annotate my function to say that it throws an exception. Again, we don't do this type of thing. So if I could scratch this off right here and say we don't do this, that's what I mean. This is not something we do in functional programming. Bad, bad, bad. And because of these last two attributes in particular, functional programmers say that a function is total, and that means that it returns a value for all possible inputs. So I do state that right here, but I think it's helpful to say that that actually includes both of these 2 points right here. So as a result of these definitions, we can say that examples of pure functions would be something like getting the length or the checksum of a string. So if you can imagine that we have A, B, C, C, D, and then we want to call length on that. You know, the length on that is always going to be 4 and so on for every string that you could possibly pass in. We'll always get the exact same result. We'll always get a result. If you think about the length function over here, it will meet each of these definitions up here. So that's why it is a pure function. You can also think of calculating the sum of a list of integers as being a pure function. Many mathematical functions, such as sine and cosine, are all pure functions. And one thing I will note about pure functions is they always have input parameters and they never return units. So a pure function is always going to have at least one input parameter, and it's always going to have a type over here that is not unit. If you see unit over here, that's kind of a bad smell that this function is doing something, right? Because if you can imagine passing data in here and then you get the unit type right here, I referred to that earlier as a black hole. Data is coming in right here and then it's disappearing, because we get unit back. That means that the data went somewhere else in the outside world. So pure functions should always have data types here and here that are not unit. And then I show a few more example signatures up here. And then a really cool thing about pure functions is that their signature tells you exactly what it does. And you can often guess what a function does just by looking at its type signature, even if the function name is meaningless. So in this example, I ask, what do you think that this function does right here? It takes a string as an input parameter and it returns an int. And then I don't show the body over here. So the question is, given this function signature right here, what do you think that this function could possibly do over here? And if you think about it, there's a limited number of things that it could do, like the things that come to my mind. Well, it calculates the length of the string that is given, returns that as an int. Maybe it calculates some sort of checksum or a hash on the string it's given to return an int. Some other suggestions I got was, if you're given a string, it could count the number of lowercase characters, could count the number of uppercase characters, could count blanks, etc. But there's a very limited number of things that this type of function can do, and you can think about those in your head. And if you know enough about functional programming already, you know that f cannot be a string to int function. And that's because if we come over here and we say to int on something like that, it will work. But if we come over here and then change that, you'll see that trying to convert this string to an int throws a number format exception. So that would violate this rule right here. And the way you would handle this situation over here is for it to be a string to int, we would have to use some functional error handling. And if it was a string to int function, it would have to return either an option, a try, or an either, based on what we know so far. It could also return an IO data type over here, like a ZIO. But because of this exception over here, this function here could never be a string to int function. It would always have to have some kind of wrapper around the int, like these right here. And the cool thing about these error handling types is that when you see them right here, you can instantly think, aha, something can go wrong inside this function body over here, like this over here. So that's a cool thing about these wrapper types. And then getting back to my point, a really cool thing is that you can look at this and you can say, well, it can do this, it could do this, and it could do some of those other things that I talked about, but it cannot be a string to end function because it does not have that wrapper right there. So in summary, what I was trying to do is give you hopefully a pretty good definition of a pure function. And this is my definition right on this page right here.